on an introduction to electric flux. And this concept is super important as we establish and build our understanding of electromagnetism. And this is actually stemming from the last video, and it's going to be another stepping stone in understanding how to pinpoint a location within an electric field and determine what that strength of the field is. Now, at the end of the last video, or some point in the last video, I had a sphere drawn around the source charge. And let's call this source charge a positive source charge. And then I drew this attempt at a sphere to kind of show you three-dimensionally that at any point on that sphere, there we would have the same strength of electric field because it's an equidistant radius to any of these points that we would make. Now obviously two-dimensionally it doesn't look like that, but it's supposed to be representational. So that's something that's super important. And what we had talked about was the fact that if you colored in a Sharpie square on a small balloon and you inflated the balloon, the square would end up, let's say you inflated it 4 times the radius, the area would end up being 16 times the area that it was before. Now the whole thing that was pretty interesting was that this bubble was an imaginary surface. So an imaginary surface was just to help us visualize that at any point on that imaginary bubble you would have the same value for the electric field. Now, the imaginary surface doesn't have to be a sphere. There can be lots of other shapes that we could use, but it makes sense that if you're trying to draw an imaginary surface where the electric field would be the same all around it, it would be a good idea to mimic the shape of the thing that you're encasing, because then you could have the same distance to all points away from it. So let's go ahead and define what electric flux actually is and how it connects to this idea. Electric flux is defined as the amount of electric field passing through a surface. Now we're saying a surface, but here specifically we're meaning an imaginary surface. And we're going to see what the heck that even means. So the amount of electric field that is passing through a surface. So I have an image over here that we're going to use to analyze that. So here we have 16 electric field lines. So in blue, those arrows are the electric field. And in green, this is our area, our surface. Now this is not a closed surface, right? It's just a square that we can see the electric field is passing through. And so we could actually calculate how much flux there was, how much electric field is passing through this surface. And we're going to get to all of that in a minute. Now, the symbol for electric flux is the Greek letter phi, or phi, and it's spelled P-H-I, and it looks something like this. Sometimes in shorthand you see it drawn kind of messily like that, but most of the time we're going to see it this way, and we're going to subscript it with an E, because we will also get magnetic flux later on down the line. Now what we're going to say is that based on its definition, the amount of electric field passing through the surface, the electric flux is directly proportional to the amount of electric field, so the strength of the field. And electric flux is also going to be directly proportional to the area. So you can imagine if I made this area smaller with the same field, less field lines would be going through it. And so what I'm going to say then is that the electric flux is also directly proportional to the area. And so what we're going to end up with is an equation where we have the electric flux is equal to the electric field times the area. Now I've specifically put a dot here because this is actually going to be a dot product between these two vectors. And you might be thinking, how the heck do you have an area vector? And that's what we're going to spend some time talking about. So over here is our area. And as I've said before, a vector is something that has a magnitude, so it has the size of the area, but it also has an orientation. And I want you to think of it as orientation rather than as direction, because it's not moving in any direction. It has a specific, it's oriented in a specific way. But its orientation is going to be something that we really need to kind of build up. And so what I'm going to do is I'm going to say that if you imagine a square sign and I have the word flux written on one side of the cardboard but not on the other side, we would say that maybe this is the front face and then behind there is the back face, and they're different, right? But the cardboard could be oriented in many different ways. So I could say that it's right now, the way I've drawn it is it's pointing out towards us, right? It's oriented with its face pointing out of the screen. Now if I look at this over here, there's no way for me to give an absolute orientation to this orange square or to this green square. But what I can say is that this square is oriented in some way relative to the electric field lines. So what we're going to look at is the orientation between E and A. So the orientation is oftentimes given with an angle, theta. Now, we would say that this thing is facing in the same direction as the field lines. And so it's not 90 degrees, right? But actually 0 degrees. So that means that I need to draw an arrow coming out of the surface that I'm going to call the area vector. Now this red arrow that I just drew there is going to be an arrow that is normal to the plane, normal to the area. And normal, remember, just means perpendicular. So that is the direction that the area is facing, right? That's how we would show it. So if I was trying to show something pointing out of the screen here, I would draw a dot. And if I was trying to show that it was pointing into the screen, I would draw an X. So that's another terminology that we use. The dot is out of the screen or the page, and the X is into. This is like looking at the back of an arrow, right? If it had a little tail on it, that would be the back of it. And if it was looking at us, we'd see the point or the front of the arrow. So this is just a way that we show that. So if I look at this plane over here where it's tilted backwards, I might draw the area vector kind of pointing upwards, sort of. It's a little hard to draw here. But you can see that it's tilted itself, right? So the angle went from being 0, the angle between the area vector, the red arrow, and these blue electric field lines, to now it's some angle between them. So when we're looking at this dot product, what we're saying is we want to know the amount of electric field that's only parallel to the area vector. And that's why we have the dot product, right? Because what it's saying is if I were to isolate just one line of each here, I might say here's my area vector and here's my electric field vector, and the angle between them is some value theta. But I only care about the amount of area that falls along the electric field. I don't care about the portion that's falling perpendicular to the electric field, and that, remember, is known as the dot product. So we only want to know how much is in between it. And if you think about it, it makes sense, because when you have to just keep thinking that the face, right, is perpendicular to the surface, right, or this arrow pointing out, so that's the direction. So we would say that the most field lines will pass through this particular area when there are 0 degrees between an area vector and electric field vector. And we know that that's a dot product because the cosine of 0 degrees is 1. It's its maximum value. whereas the cosine of anything that's greater than 0 degrees is going to be less than 1. So if you can think of this, if I laid it completely flat like that, so it was completely flat, that would mean that the area vector was pointing at 90 degrees to the field line. So if I were to pull that out, I'd say here's my electric field vector, here's my area vector, and they're at 90 degrees, and the cosine of that configuration would be 0. In other words, there would be no field lines passing through this green surface if I lowered it even more flat so that the plane lay along the field lines. So you can see here that the electric flux, when we give it its full definition, it looks something like this. The electric flux is equal to E dot A, which is the same thing as saying E times A times cosine of theta. Now this is going to become extremely important when we start to develop our understanding of how we will use this to determine the strength of the electric field at a particular location, or how to determine how much charge is creating the electric field. And so this term flux, which is the amount of electric field that's passing through the surface, has to do with how the surface is oriented relative to the field lines, and how big the surface is, and how strong the field is. So all of those things are contained within this flux equation. I know this is a very new concept for a lot of people and can be a little bit confusing, so take some time to familiarize yourself with this, because as we go, we will just be adding to this concept.